So the definition of the definite integral, I have to kind of explain and give parts. Don't worry about writing down what's down here. Don't really worry. Sorry, I know you're getting really involved in that. This is more, I want you to pay attention kind of what I'm doing right now. Okay, so I want to find the definite integral of a particular thing. So I've got a function f of x, and I'm going from a to b, any a to any b. And I want to find the integral of f of x from a to b. I want to find the area under the curve of f of x between a and b. Okay, like we've been doing. That's what we did yesterday. That's what we did in here on Tuesday. We took rectangles and we estimated using rectangles. Right rectangles, left rectangle, we used the RAM method. That works really good. It really does. It's a nice way to do it. Why do we use rectangles? Because rectangles are easy. Now, what we're going to do is we're going to do the same thing. We're going to take this space between A and B and partition it into rectangles. That's what we're going to do. We're going to partition it into rectangles. And, so we're going to have lots of rectangles. They don't need to be equally spaced. And we're going to go, our first rectangle, this value here, A, we're going to call it x sub 0. Remember, subscripts have nothing to do with value. Subscripts just let me use multiple x's, use the same variable repeatedly. Okay? And our last variable, b, our last one is going to be x sub n, because it's n partitions. We don't know what n is. N could be 3, n could be 3 million. We don't know. Okay, so if we have x sub 0 is here, x sub 1 is the one next to it, the one before x sub n is x sub n minus 1, one less than the last one, and so on. And we're going to work your way from the end to the end. Pick some partition in the middle. Somewhere in the middle. We don't know what this is. It's somewhere in the middle. Anyone in the middle. And it could be the first one, it could be the last one, it could be anywhere in between. Okay? This is going to be a typical rectangle that we're going to have. Okay? And it's going to go from x sub k to x sub k minus 1. That's the difference. Okay? And so we're going to make a rectangle out of this. The first thing we do when we make a rectangle is we come up with a width. And our width that we get from this is, x sub k minus x sub k minus 1. You take the x value, subtract the x value before it. That's how wide that rectangle is, right? Okay. Because it's a random one, we're going to call that delta x. That's our change in x, delta x sub k for our kth interval. Okay, so for that interval, our kth interval, some interval k in the middle, n equals k. For that interval, delta k, that's our width. It's the change in x. Delta x. Delta x sub k, it's the change in x. That's our width, delta x. Okay. Now, if we want to find the area of a rectangle, we have the base. We need the height. So we're going to pick some point in between those two x's. And it doesn't matter. It could be the middle. It could be the right. It could be the left. It could be anywhere in between. Trust me, it doesn't matter. It does not need to be in the middle, right or left. It could just be any point between them. That's where our top comes from. That's x, or that's c sub k. That's the point in the middle, and you'll see it down here, c sub k. And our height, what do we do to find the height? We take that x value, plug it into our function, right? So our height is f of c sub k. Are you with me so far? So I've taken a rectangle, a random one. I have its width, I have its height. The area of that particular rectangle is f of c sub k times delta x sub k. It's the height times the width. That's what that rectangle is. And what do I do if I want to find the area underneath the curve? I add up all the rectangles from k equals 1 to n. In case of 1 is the first rectangle. In case of n gives me the last rectangle. I want to add them all together. That's the sum, right? Adding all the things together. That's what we want to do. We want to partition that curve into rectangles, and we want to add all the rectangles together. Add the rectangles together, what do we get? We get an estimate of the area, which is what we did. When we were doing this yesterday, n was 4. Generally speaking, for most problems, n was 4, but for a couple of other ones, it was a little bit larger. But n was 4. What we're going to do is our integral, our definite integral, is defined by doing this. Okay? If we make the interval lengths tend towards 0, in other words, and this, let me explain this, and you will need to get this down because you're going to need it to do some of your homework problems. Okay? The definition of the definite integral, the integral from a to b of f of x dx, is the limit of, and that is not the absolute value. The double bar on p does not mean I'm taking the absolute value, because that would be stupid anyways, right? Taking the absolute value, that'd be useless and wasteful. No, what this means is as the norm approaches 0. So the norm approaching 0 means the largest rectangle is approaching 0. The largest width is approaching 0. So as our biggest one goes towards 0, what's happening to all the rest of them? They're even smaller, right? So we're taking the limit as our biggest rectangle goes towards 0. So if our biggest rectangle width goes towards 0, not the area, but the width of the rectangle, as our biggest width goes towards 0, that means all the other widths are even smaller than that. Because if we take this biggest one and make it smaller, oh, so the next big one is smaller, and it gets smaller, and it gets smaller, and it gets smaller, smaller, and it gets smaller, and it gets smaller. We're going to take all these infinitely tiny rectangles and add them together. That's the definition of an integral. This is technically a Riemann sum. And it'll be up on the next one. But that's what a Riemann sum is, you're adding up all these rectangles inside. Now, on the AP test, they say use a Riemann sum. What they really mean is use the rectangular area method. It's the same thing. Find the rectangles. But this is the definition of an integral. So you know what we're going to be doing when you guys do integration? What you're learning how to do in this chapter is add up an infinite number of items and come up with a specific value. Technically speaking, you're adding up an infinite number of extremely narrow rectangles. Because as the largest one goes towards 0, that means you have to add another rectangle. You have to add another subdivision in order to be able to get the biggest one be to 0. So you keep adding numbers of rectangles. Eventually, you're adding essentially an infinite number of rectangles together. That's what one of the things you're doing. You want to blow somebody's mind. When you do an integral, you're actually adding up an infinite number of extremely narrow rectangles and coming up with a specific value, which is really cool. Okay, so this is a definite integral. So a couple of your homework problems is going to be taking the Riemann sum, rewriting it as a definite integral. Okay, taking the sum here and writing it as a definite integral. Okay, so if I look at what I have here, I want to take this, rewrite it as an integral. So I have the integral. Where do I start my integral? Where does my interval start at? -7. So I go from -7 to where do I end? 5. And I'm taking and adding up, this is my function. I'm taking c sub k squared minus 3c sub k. Well, this is actually a function. C is a specific value of x, but I don't want a specific value of x. I want to use a generic value of x, which means I just take c sub k, replace it with x. So it's the integral of x squared minus 3x. delta x is the same thing as dx. That's what the shorthand dx actually stands for, is for delta x, the change in x. That's it. So that homework problem will take you all of about 3 seconds to do. 5 or 6 of them take you all of about 20 seconds to do tops. Because all you do is you go from where it starts to where it ends, and take the c's, replace them with x's, and take delta x and replace them with dx. You're just rewriting the sum as an integral.
Would it be, wait, is k always equal to 1?
No, k is just some value. No, this is some k equals 1 to n. So k sub 1 is the first one, k sub 2 is the second one, where k increases in value over time.
Would there be parentheses around like the x squared minus 3x?
You might or might not. That's a very good question. I don't worry about it, because here's the beginning and end of my integral. This is the beginning of my integral. This is the end of my integral. Everything else inside is the integral.
Okay.
So my whole function is out. I do not need to put parentheses around it. You kind of do here, because of the way the notation works, but when you get to integration, you don't need to worry about that. As long as you've got a dx at the end, you know where it stops, or dy or dz or d whatever.
So did you sub in x for c?
C sub k. Yep, that's all you have to. That's all you have to do on this.
So,
Literally, that's all you have to do.
So you didn't sub in x for c and then 1 for k. All right.
Nope. No. This and that are the same. The integral means exactly the same thing as all of the rectangles added together.
Got it.
I'm not doing one specific rectangle in here. I'm doing all of them. 2 ways of writing the same thing. Adding up all of the rectangles, adding up an infinite number of rectangles, is what the integral is. We say the integral of f of x from a to b. This is how you pronounce it. This is how you say it. Please say with me. The integral of f of x dx from a to b. I did not hear everybody. I want to hear everybody. There was at least one person not talking. I want to hear everybody. The integral from f of x dx from a to b. Thank you. It is important. You want to get the notation correct. You also want to sound like you know what you're talking about when you say it. The integral from a to b of f of x dx. Now, when we start putting values in, you can obviously say that. Integral of, okay. Now, there are some important things that we need to talk about here. What this is, the notation, and explain the notation. Okay? This is the integral symbol. When we take the integral, you use the integral symbol. Looks kind of like a little cleft note kind of thing, right? It's not quite exactly that, but that's what it looks like. This number down here, whatever it is our lower bound. That's our lower bound. And we always go from our lower bound to our upper bound. And it's always our lower bound to our upper bound. Always from the bottom to the top. Always. From A to B. If it's got numerical values, you say the numerical values in that order. That is important how you do that. This is our function of integration, also known as our integrand. That's the function we're integrating. And this is the variable of integration. Ran out of room. Sorry about that. Deal with it. Variable of integration. kind of like you can have a derivative with more than one variable in it, but you only derive with one variable at a time. Same thing. We only integrate one variable at a time. You generally will not have in this class more than one variable at a time. It will be dx or dy or dr or ds or d theta. It will be one variable that you are integrating with at a time. You may have constants of unknown values, but they will be constants, not variables. So if I take the integral of ax, a is a constant, x is the variable, a is a constant value. And we treat it just like we would treat any numerical value that is constant. Okay? So you only do one variable at a time. The variable you're dealing with is dx. You do not get to multivariable calculus until you are in third semester of calculus. So even when you go to college, you won't have that first year. Okay, few rules. Integrals of a constant. If f of x equals c, a constant value, on the interval from a to b, then the integral from a to b of f of x dx is equal to the integral from a to b of c of x dx. That is the constant times b minus a. The integral of a constant is the second easiest integral you will ever do. The second. There is one that's easier. Okay. The second easiest integral is the integral of a constant. Because basically it's that constant times the upper bound minus the lower bound. That's it. But think about it. When we first started this on Tuesday, what did we talk about? We had moving at a constant velocity. We had a constant function, straight line. What did we do? We took that straight line height times the difference between our start and our end. If it's a constant value, it's a straight horizontal line, you've got a rectangle. The constant is the height of the rectangle, b minus a, the upper bound minus the lower bound is the width of the rectangle. You get the area. So for example, evaluate the integral from 3 to 7 of negative 20 dx. That's negative 20 times 7 minus 3. Okay. 7 minus 3 is 4. 4 times negative 20, negative 80. And yes, integrals can be negative, even though we're talking about area. I know. How are you saying to yourself, Mr. Orris, how can you have negative area? Oh my God, we have negative area because what did we do? We added up a bunch of rectangles. We found the area of the rectangles. We added up an infinite number of rectangles between 3 and 7. That's what we did, and we came up with a negative value adding up a bunch of rectangles. And I know you're thinking, Mr. Orris, but rectangles have an area. The area is always positive. It's positive. Nah. I know, like I said. Okay. Area under the curve, evaluating it out. Okay. Area under a curve method of evaluating a definite integral. If y equals f of x is a non-negative and integrable, which is much harder to say than differentiable. I'd much rather say differentiable than integratable. Integrable. This doesn't roll off the tongue. Over a closed interval from a to b, then the area under the curve y equals f of x is the integral of f from a to b. Okay. Now, the area is equal to the integral from a to b of f of x dx when f of x is positive, when f of x is greater than 0. In other words, when the function is above the x-axis, the area between the x-axis and the curve is a positive area. That's what that first one says. When from a to b, the integral from a to b of f of x is equal to the area is equal to that, the integral is equal to the area underneath the curve between the x-axis and the curve when f of x is above the x-axis. When f of x is below the x-axis, the area is negative. Above the x-axis is a positive value for the integral. Below the x-axis is a negative integral. Considered negative area. It won't always be that way, and you'll see later on, but we don't get to that until chapter 8. But for using area to define an integral, we use above as positive and below as negative. That's how you can get a negative curve, because we did negative 20. Negative 20 is way below the x-axis. That's why we got a negative area, because f of x, the function we were evaluating, was below the x-axis. Anything above is considered positive, anything below is considered negative. It is entirely possible to have an integral of 0. If the area below and the area above are equal to each other, what's my integral? My integral would be 0. There are other ways to get 0 integrals, and we'll hit those coming up. Okay. Yeah, so in general, area above the x-axis minus area below the x-axis. That's generally speaking what it is. We are going to use several methods for integration. We've already done one, technically. When you guys were using the rectangular area method, you were doing an approximation of an integral. Not a very good approximation, though. Right? Because how many rectangles did you have? You only had 4 rectangles at a time, not an infinite number of rectangles. An infinite number of rectangles is so close we actually call it the exact value, not an estimation anymore. But when you use 4, that's an estimation. Okay? There are other ways of doing this. We will learn ones to do it no matter what, but the ones we're going to work with today are actually calculating the area using our geometry skills. What did the little acorn say when it grew up? Geometry. That's a dad joke. It's really stupid and sucks, but you laugh anyways. I actually haven't seen it. It's fine. Okay, here we go. So, I cannot tell you enough how important it is. I cannot tell you enough how important it is when you're doing today's problems to draw a picture. Do not draw this tiny little thing that nobody can see except for you and me with a magnifying glass. Draw it large enough that you can label and mark on, because that's a real issue. I do see students, I'm just going to draw this little graph here, and I'm going, okay, but you can't label it because there's no room to label things. You're going to need to be able to label things. So what we're doing is we're going to evaluate these using area. So you have to kind of know what some of these things look like. So my first one, my function, 16 minus x squared. It's a semicircle with a radius of 4 centered on this, in this case, in the origin, so it goes from -4 to 4. That's what f of x is. That's my function. The square root of 16 minus x squared. And it has a radius of 4, so this y-intercept is also 4. You must recognize that the square root of some number minus x squared is a semicircle with a radius, the square root of whatever that number is. You need to know what that looks like. You're going to see that often enough. You need to know that. Now, so that's what f of x looks like. What is my integral on this one? Where do I go from where to where? I go from -4 to 0, which means I want to figure out what this area here is. How much of a circle is that? 1/4 of a circle. So I want to have my integral from -4 to 0 of the square root of 16 minus x squared dx is equal to 1/4 the area of a circle with a radius of 4. Because I have a quarter circle. And my circle has a radius of 4, so the area of that circle is pi r squared. Pi times 4 squared is 1/4 of that. So my integral is 4 pi. Okay. Does that make sense? Do you see why drawing a picture is so freaking important? It is very important to draw a picture. Very important to draw a picture. If you're not sure what something looks like, pull out your graphing calculator or pull out your cell phone and use Desmos on your cell phone to draw the graph. Okay?
So we should like graph it.
Even if it's something you know, you should, because you want to get used to seeing that picture. You want to have that visual connection between the integral and the area. That also helps an awful lot as we're moving through. You're not going to do it all the time, but for the stuff today, when you're evaluating using area, you want to make that strong connection. Because there will be times when you'll be given the graph and asked to integrate. You won't know what the function is, but you have a graph to work with. And you have to remember, oh, it's the area underneath the graph. And you'll have to be able to make that connection because you won't have the function. Here's a graph of f of x, but you won't have an equation. And you're going to want to integrate. You're going to have to go back to this. You go, I forgot how to do that. No, we did this early on. Okay? So I've had students, you never showed it. Yeah, I did. I showed you this. I showed it to you here, remember? Oh, that's right. Yeah. Once again, particularly with integration, the latest thing you do is not always the best method to solve a problem. Okay, we'll come up against that really big in chapter 7. Okay, so I'm just extending to move it up. Want to do the same thing here. Draw a graph. And I'm going to go ahead. This is a nice straight line. However, I do want to put marks on my straight line to help me graph it really good. And you'll see why in a minute. Okay. So the graph of x plus 1 looks like that. And where are we going from? -3 to 2. So we're finding all of this area here. Uh-oh. Got an issue, don't we? It's not really easy like the last one. Everything was all above the x-axis. Not all of it's above the x-axis. Some of it's below the x-axis. So we have to partition it. Where is this point where our break is? Right here at -1. So when we're solving this problem, our integral from -3 to 2 of x plus 1 dx is actually this triangle above minus the area of the triangle below. The area above the x-axis is positive, the area below the x-axis is negative. Find the areas of the two triangles, subtract one from the other, and you've got it. What is the formula for the area of a triangle? 1/2 base times height. Okay, so for our first one, it's 1/2. Our base, it goes from -1 to 2, so that's 3. And our height goes, okay, at 2, how tall is it? I plug 2 into the function. 2 plus 1 is 3. So there's the area of the first triangle. Base times height. Minus 1/2 times the base of the second triangle. It goes over from -1 to -3 is 2 units. And how far down does this go? If I plug in -2, plug in -3 into there, -3 minus 1, it goes down to -2. So I have 2 units that it goes down. So the first triangle has an area of 9/2. The second triangle has an area of 2. 9/2 minus 2. 5/2. Okay. Does it make sense? This is not how we're going to do everything, but this is a good start. Okay, a good start on how to do stuff. Get out your graphing calculators. If you do not have a graphing calculator with you, you'll just need to make sure you have notes of how to do this. Okay. Because the next one is how to do it on your calculator. Now, oh crap! I forgot what the answer was for this one. Well, I always like to give one that I know what the answer is off the top of my head, and I do actually. I think I can figure this one out, but I don't want to do it off the top. I can do it. Give me a couple minutes, we'll do it. Okay, so we talked about how to do numeric derivatives, and hopefully you figured out how to do numeric derivatives on your calculator. You need to know how to do numeric integrals on your calculator. Once again, there are 4 things that you need to know how to do on your graphing calculator for the AP exam. And only 4 things is your graphing calculator useful for. Okay? Solver, graphing, that's why it's a graphing calculator, numeric derivative, numeric integral. Okay? And there will be times when you have your calculator portion of the test, you are expected to do the numeric integral because doing it by hand is either basically impossible, because there are times when it's impossible to do by hand. You can always do a derivative by hand and then plug the values in. It's not always possible to do a numeric integral by hand, at least not in the method that's decent, and you'll need to use your calculator. On multiple choice, if you have the calculator multiple choices and the answers are decimals, oh, you better pull out your calculator or you're screwed. Okay? Now, in your textbook, Ender, I believe you saw this, Ender, that was the numeric derivative. Ent, or nint, is the numeric integral. If it says use int, that means pull out your calculator and do the integral by hand. I mean, do the integral on your calculator. Okay, now, because everybody's calculator is different, and every calculator in here, well, not every calculator, but I'm sure there's at least 5 different types of calculators in here. And even within the same family of Texas Instruments, they don't all do it the same. And there are a couple of ways to do it. Generally speaking, there are 2 main ways of doing the numeric integral on your calculator. First, you have to find on the menu, and it's usually under the calculus menu, okay, numeric integral. And it'll be n-ert, or it'll be the integrand sign, and it'll have n with the integral on there. Okay. So if I want to find this, it's usually fn integral or something like that, or n int, or something along those lines, depending upon which model you have. One of 2 things will pop up. Either you will get a oh my God, I'm forgetting the exact term. You'll get a template, that's it, a template of an integral with spaces to type in your lower bound, upper bound, and the integral. That's a nice one, because then you'll just type in exactly what you see here, and it'll pop it up, and then you hit enter or solve, and it will do it for you. Other ones, you get fn int, and then what you have to do is you have to type it in the way it appears here. Type in the function, type in x, because you have to tell it the function you're integrating, you have to tell it the variable you want to integrate with respect to. And then your lower bound, and then your upper bound. What? Pi over 2. Yes, that's pi over 2. So if you are actually, once again, you can either, if you get, depending on what type of calculator you have, you will get a template where you just fill in these values in that template, or you're going to have to type in cosine x, comma, because you have to give it the function. X, you have to tell it the variable you are integrating with respect to. Comma, the lower bound, comma, the upper bound, end parentheses. It is not always the easiest thing to do. If you don't type it in correctly, it won't work. Now, who's done this? What'd you get? You got 1? Let's see, so it would be negative sine. The antiderivative of cosine is negative sine. So negative sine of pi over 2. Sine of pi over 2 is 1. No, sine of pi over 2 is 1. Minus the sine of 0, which is 0. Should be negative 1. I'm doing it in my head. Sorry, I'm just trying to do it in my head, and I'm a little rusty on doing it in my head. So let me go ahead and pause this.